Hi, this is Shawley Physics, episode on potential energies and non-conservative versus conservative forces. In this episode, we're going to see where potential energy comes from the work kinetic energy theorem, and also look at why only certain forces have a potential energy associated with them. So just the first force that we tend to gravitate towards is gravity, of course. So we'll look at that gravitational force. As we lift up an object from the ground to some height, it's going to change its vertical position there. It's going to have a delta y associated with it. So there is lifted up. And as we do that, we're doing work to the object, and gravity also does a negative work. And we know that because as we do work to an object, it's supposed to change its kinetic energy. It's supposed to speed it up or slow it down. In this case, when you lift something up, it just kind of remains in your hands. It doesn't really go flying upwards, usually, if you're just trying to lift it. So whatever energy you put into it, it's going somewhere. That kinetic energy is no longer there. That means another force is doing negative work to it. Of course, that mysterious force is gravity. So the work done by gravity, when we lift it up, we've got a displacement upward, and that gravitational force is downward. Of course, it's of magnitude mg, whatever the mass of the object is, times 9.8. So we have a force associated with it. We've got a displacement. We also have an angle between those two vectors. Weight is downward, and the displacement is upward. So let's put those together. The force involved is mg, that's the weight. Our displacement is delta y. And we've got a F times displacement times cosine of the angle between them. So our angle here is cosine 180. And just simplify that out a little bit. We have an mg delta y. And the cosine of 180 makes this a negative. So this is negative work done. There's the gravity. As we lift it upward, gravity does a negative work to that mass. All right, so now if we have this negative mg out front, what is the delta y? It's a change in position. So if we call this position 2 up here and position 1 at the bottom, this would be a y2 minus y1. That's our change in position. And now if we distribute that mg inward, what I'm going to do is just keep this negative on the outside for a moment. But if I distribute that mg to the y2 and then the y1, we'd have an mg y2 minus mg y1. There it is. All right. So this is kind of curious. The work done by gravity is mg times the height, or the position 2, minus that original. Now if y1 is 0, if that's our lowest point, then all we'd have left here is mg times the height that we lifted up. So if we define something here, sort of like we defined kinetic energy in a previous episode, kinetic energy is 1/2 mv squared. And that just appeared out of this work kinetic energy theorem presentation. It just appeared in the equation. I'm going to call this creature here mgy. It's an energy. It's a work done by gravity. So it's associated this energy amount with a force based on its displacement, the object's displacement. So I'm going to introduce this letter. This is U, stands for potential energy. Potential energy. And in this case, we're going to label it G because it's potential energy due to that gravitational or weight force. Just in general, we're going to call it mgh. Now H can be like a height position. In this case, it's a y position. But usually that H is usually very helpful in dealing with objects that are being lifted up or they're falling down. What height position, what altitude are they at? So if we keep that in mind, if we substitute UG for this MGY or MGH, first just to make it relate better here. We're going to change those y's to a height position. All right. So now if we substitute UG in here, just what we're calling MGH, we get a UG at position 2, the potential energy, gravitational potential energy at position 2, minus the gravitational potential energy at position 1. And what is a final minus an initial? It's a change. So we get back to a negative change in potential energy. And this would be a gravitational potential energy. But just in general, what we're seeing here is that when work is done by a force like gravity, a force that causes a potential energy, or a force that can store energy. And if you think about what gravity does, it does store, in essence, at least in concept. If you lift an object up, it's not moving up here. There's no kinetic energy left. But is that energy completely gone? No, I can release it and it starts to move again. Now, that's kind of different than friction, because if you push an object along a surface and it slides, then it'll actually stop and it won't come on back, right? So if you shove a chair across the floor, it doesn't slow down and then come back to you. But if you toss an object up, it slows down and comes back to that starting position. So that's where we can get a sense of when forces produce a potential energy kind of effect, when forces store energy. So we have one more piece to our work equation. And work causes a negative change in potential energy. And we have also introduced something, we've defined what's called gravitational potential energy. Now, what's another force that may cause a potential energy to happen, energy be stored, in essence? Now, is the spring force. Now, just as a reminder, the spring force, according to Hooke's law, is negative K times the elongation of that spring. We called it the spring displacement. So as I pull the object, this mass here, to the right, all right, what's going to happen then is the spring elongates. Just want the spring here. It stretches out with that object. Okay. And as it stretches out, if there's a displacement to the right of delta x, then there's going to be a force acting back to the left. That's the spring force. That's where the negative nature comes in here. Next, what is going to be the work done by the spring? So work done by the spring. Now this work is position dependent, so we can't just use F times x. We have to use integral of F dx, because that F is a position dependent expression. Now this x and the F are vectors as well, and there is an angle between these vectors that is non-zero. We have a non-zero angle. It's 180 degrees. So we should consider also here, let's clean that up a little bit. We're going to take the force dot dx, and dot dxing, we're going to have that cosine of theta in there, so that'll include a cosine 180 right in there with respect to x. And we're gonna stretch this out from some initial x position to some final x position. So I'll call it 0 and 1. So we'll go from x0 to x1. All right. Simplifying a little bit, what's this cosine 180 going to do? It's going to put a negative out in front. So we'll have a negative kx dx from the original position to the final. It's an O. And now we're ready to integrate. So when we integrate that, we get a negative kx squared divided by 2. We'll evaluate that from the original x position to the final, and plugging that in. Again, I'm just gonna keep this negative out front. See what happens. So another way we can write this little creature here is 1/2 kx squared. So I'm going to put a 1/2 k, and we plug in x1, we'll have an x1 squared minus 1/2 kx initial squared. There it is. Okay, now at this point, again, I'm going to pull out the potential energy of the spring. Okay, so the potential energy of the spring, we're going to define that as 1/2 the spring constant times the position of that spring, the elongation of that spring squared. And so this is something we'll use again, just like the gravitational potential energy. There's a spring potential energy, 1/2 kx squared. So if we just use that concept now, again, we're going to arrive at that work done by the spring is negative us, or us1 minus us initial. Okay, so we get it showing that the change in potential energy, the negative change in potential energy, is equal to the work done by the spring. This is a characteristic of conservative forces. Conservative forces. So gravity and the spring force, they're conservative forces. If you pull an object out on a spring, what happens when you let go of it? It slings back. All right. If you shove it inward and compress that spring, what's it do? It pushes back out. It tries to return that object back to where it was before. The energy that you put in is the energy that it releases back. Okay. So let's compare this now to a non-conservative force, like friction. All right, if I take this object and I drag it right across the surface there, and I displace it, there's going to be a displacement of the object. We'll call it delta x. And now what we're talking about here is that there's some friction. I'm going to say there's a mu of, I don't know, 0.2 or something like that, okay? So there's some friction here. And we're moving at some kind of position. So I just wanted to, we're not really going to bring in numbers here, but I'm just going to show you that there's a non-zero mu. There is some friction here. And as that works, there's a friction force to the left. So there's a displacement to the right and a friction to the left. So when we find that work due to friction, we're going to have like a mu times normal force times the displacement. And then the angle between them is 180 degrees, cosine 180. So we find that the work due to friction is a negative mu times normal force times that displacement. All right. So does that mean we have like a conservative force here? Is this like a negative mu Fn x final or x1 minus mu normal force x2? Can we call that the potential energy from friction? Actually, no, because what's a little bit different in this case is that when you push an object forward, it comes to a stop due to friction. It doesn't come back at you. It's like that chair. You push a chair away from you, it doesn't sling back towards you. Friction doesn't do that, because if I now push this box to the left, friction acts to the right. See, the friction changes direction. It's always opposing the motion of the object. It's not ever helping the motion. If we go back and look at gravity, if you push an object upward and release it, it comes back down on its own. Gravity pulls it back down. So when you push an object out along the floor and friction slows it down, friction doesn't sling it back. So gravity is always downward. That's the difference here. You lift an object upwards, gravity's down. You drop an object downwards, gravity's down. Gravity is always down. It's always bringing that object back down. How about the spring force? If you pull an object to the right, like you see here, the spring is going to pull it back to the left when you release it. If you shove a spring to the left, it's going to push back to the right. It always tries to return that object, sort of like gravity does. But you don't get that for friction. You don't get that for drag. So these are non-conservative forces. Friction is non-conservative. I just want to write that out there to get it in your head. It's non-conservative, so there's no potential energy associated with it. Okay, but the spring force, gravitational forces, these are conservative forces. The energy that you put in equals the energy that it spits back out. It's kind of gross, these conservative forces. They're real messy. They suck energy out, then they spit it back. It's disgusting. All right, so we got this non-conservative, like drag, friction, versus conservative forces like gravity and the spring force. This example, I'm using University Physics, is Young and Friedman 15th edition, published by Pearson in 2020. I had this question here, which I think is very, very conceptual. It's very good in terms of thinking about conservative, non-conservative forces, and actually applying and using potential energy. This is number 9 from the problems in chapter 7. We've got this rock in a bowl, and we're just letting it slide down to the bottom. So in this case, we don't just have an object dropping, it's actually translating a little bit to the side as well. So there's a downward motion and a right-hand motion from point A to B. The small rock of mass 0.2 kilograms is released from rest. So we do have an initial velocity of 0 up here. It's important to know. And so point A is at the top edge of the large hemispherical bowl with radius 0.5 meters. If that matters, we'll see if that matters later. Assume that the size of the rock is small compared to R and can be treated as a particle. This is important. Later on we get into objects that might roll and things like that, so it's not happening here. So assume that the rock slides rather than rolls. The work done by friction on the rock when it moves from A to B at the bottom of the bowl is 0.22 joules. So the work done by friction from A to B is 0.22 joules. All right, it says magnitude 0.22 joules. So you might imagine what friction might be doing. Is it going to add energy to it? It's going to increase the kinetic energy from friction, or is it going to decrease? Question A. Between points A and B, how much work is done on the rock by I, the normal force, I guess it's some Roman numeral type of thing, gravity, and B, okay, what is the speed of the rock as it reaches point B? All right, so let's try out this letter A first. And there's a couple questions after that we'll get to as well. So between A and B, how much work is done on the rock by the normal force? Okay, so the normal force at this point is pointing this way. At this point is pointing that way. At this point is pointing that way. And at the bottom is pointing straight up. So the normal force always acts normal to the surface at that point. Now, work, let's keep this in mind. One form of it is F dot, we'll use S here, okay? I'm going to use S because this is an arc length type of thing. We're moving along the edge of the bowl here. So I'm going to use S. It's better than Y, it's better than X. It's not really a radius here. So S is our best character to characterize this. If you do recall our dot product definition, this would mean that if we take the magnitude of the force at each point and the magnitude of that displacement multiplied by the cosine of the angle between them, that's going to be the work done by this particular force. And we're talking about the normal force here. So is normal force ever in the direction of the displacement at these points? At this point, the rock is going in this direction. At this point here, the rock is going in this direction. It's always moving tangent to that slope of the bowl. So the angle between the normal force and that displacement vector at each point is always 90 degrees. So if we're talking about the work done by the normal force, it's always going to be 0. That cosine of 90 degrees is 0. Okay? So if we plug in a normal force here, normal force is not doing any work to this. All it's doing is supporting a part of the weight, okay, component of that weight. So the work done by that normal force is 0 because the angle between the force and the displacement at any point in this bowl is 0. So there's no work done by normal force. How about by gravity? Well, as the rock falls, remember gravity is always pulling it straight down. So I'm going to clean this up a little bit. All right, up here, gravity's down. Down here, gravity works down. Somewhere in the middle, you got it. Gravity works down. So at point A, it is translating downward. At point B, it's not translating downward. So our big question is, how much work is done on the rock by gravity? Well, if we're now looking at gravity, its weight is mg and it's always downward. But this S component, it sometimes has velocity in the direction of gravity and sometimes less, but there's always a small component of S, except for at point B, where gravity is working on it. So the work done by gravity is non-zero, but we only need to focus on the downward component. So what is the displacement of the rock from point A to point B vertically? What's the vertical displacement? It's going to be the radius of the bowl, 0.5. That's it. It goes from the top of the bowl to the bottom of the bowl. So the radius, or the displacement, is downward. The angle between the downward direction and gravity is 0. So it's getting displaced downward from the top of the bowl to the bottom by 0.5 meters. So all we got to do is take that mass of 0.2 times 9.8. I'm gonna make it 10. So m times g. I'm going to use g of 10. All right. And we've got the 0.5 there. So that work done by gravity is going to be half of 10, which is 5, times 0.2, which is 1 joule. Oh. Okay, and that'd be 2 times a half. Yep, there we go. Is 1 joule. So work done by gravity is 1 joule. It's going to speed it up. All right, so there it is. So between A and B, the work done by gravity is 1 joule. Just reflect then on this curved surface. Even though that the path takes the rock this way, notice that the energy at the bottom would be the same as if we just dropped the rock from 0.5 meters to hitting the ground. The actual path it takes to get down there doesn't matter. Only the height matters. Only that initial height is what matters. And now recall back to our discussion about potential energy. Notice potential energy at the top would only depend on the height, and it would be equal to, the 0.2 times 9.8 or 10 times the height of the bowl. There we go. It's the same exact way to figure it out. There's the potential energy. All right, so the potential energy is equal to the work done by gravity. Woohoo! Part B. What is the speed of the rock as it reaches point B? All right, so if you have the work done by gravity, that's going to equal a change in kinetic energy. That's where velocity is always going to get involved. The work done by gravity is 1 joule, and change in kinetic energy will be half m. Man, that's a nice mass there. That's a good convenient mass, 0.2. All right, so we have 1/2 m final velocity squared minus 1/2 m times the initial velocity is 0. We're dropping the rock from rest at the top. All right, so real easy step whenever you're asked about velocity after you have the work done, think of kinetic energy. Work equals change of kinetic energy, also equal to a lot of other stuff there. Half of 0.2 is 0.1. We get a 0 over here. Divide both sides. 1 divided by 1/10 is 10. So our final velocity is going to be the root of 10. And we got root 10. 3.16 meters per second. There it is. Letter C, of the 3 forces acting on the rock as it slides down the bowl. This is a key question here. Very conceptual. Which, if any, are constant and which are not? Explain. All right, so we have the 3 forces. We've got gravity, normal force, and friction. Is gravity constant? Gravity is the weight, mg. Does m ever change? Does g ever change? They're always constant. So gravity is constant. What about normal force? What at letter A, is the side of the bowl supporting any of the weight? Nope. As it slides down, it's getting faster and faster and faster. It's also changing angle. So the normal force supports more and more of the weight until it gets to B. It's obviously going to change. It's also going to be increasing because normal force points in towards the center of that turn. So it's going to be applying a centripetal force to that rock because it's changing the rock's direction as the rock speeds up. So normal force is definitely not a constant force. So gravity is constant. We have normal force is not. And what about friction? Well, remember friction, our buddy friction. Friction is mu times normal force. So if normal force changes, the friction's changing as well. Friction goes from near nothing, so it's really easy to slip on a very steep slope, to a maximum down here, where normal force is maximum. So normal force or friction is not not constant either. There we are. Gravity is always going to be constant near the surface of the Earth. If we change that distance between us and the center of the Earth dramatically, maybe it'll change a bit, but not near the surface. Well, normal force and friction are not. And okay, so D, just as a rock reaches point B, what is the normal force on it due to the bottom of the bowl? Okay, so the bottom of the bowl. This has not a whole lot to do with work anymore, but this is a nice flashback to centripetal force. So if you don't need a reminder about that, feel free to skip past this part. However, it's a great reminder that this is a AP style question. This is the kind of thing that they might throw at you to cover several concepts on a free response question. So at the bottom of the bowl, there's a normal force, but a moment later, that rock will continue sliding up the other side of the bowl. Therefore, it's going to be continuing to change direction, and the normal force must be greater than the weight at that point, because in a moment later, it's going to be up higher. It's not going to be lower than the surface of the bowl. All right, so the normal force is going to be the apparent weight of that rock. And we apply Newton's second law at this point. Let's not forget about how to do this. Normal force is up in the direction of the turn minus the weight downward. I'm going to substitute mg for force due to gravity. And this acceleration at this point is all centripetal. It's not getting faster or slower due to gravity at point B. So the only acceleration is centripetal, and it's upward. So we're going to substitute v squared over the bowl's radius there at the bottom. All right, so we're trying to figure out the normal force. That's going to be mv squared over r plus mg. And we can work all that out. 0.2 is the mass. We now have the velocity of 3.16. We're going to square that, which is 10. Lucky us. R is 0.5, and we're going to add 0.2 times, I'm going to use the G of 10 again. It's a little easier for the math. It's 20 times 0.2 is 4, plus 1 more. We should have 5 newtons of force. Hopefully I did that right. I'll do a quick check. Good thing I did the check. Mental math was a little off. 6 newtons, there we go. All right, that's surely physics for you. All right, I do make mistakes. So I hope this has been a kind of capturing a lot of different concepts here. Whenever there's a potential energy involved, the particular path it takes doesn't really matter as much as displacement in the direction of the force is what matters. And that's what really came out here. That the path from the rock from the top of the bowl to the bottom of the bowl didn't really matter. It could have squiggled up and down like a roller coaster. But as long as we're comparing point A to B, all that matters is the distance, that horizontal distance, that height. I'm just using my mouse instead of my pointer. That's great. Way to go, Shelley. Well, I hope this whole presentation has been more helpful than those last few moments, but I hope you take care and live up to your potential. Bye.